Hello, good morning. So this is the last lecture on graphs, and I will be talking about graph foundation models. Before we move on to that, maybe a few words about foundation models. There's an ongoing debate as to how to define these models and what are their boundaries. So here I'm quoting the definition from, or the description from the Stanford Institute for Human-Centered AI. Any model that is trained on broad data that can be adapted to a wide range of downstream tasks. Yeah. Previously, it was mostly understood as large language models, and the criticism in this was, okay, large language model is too narrow in that it's only focusing on text and language, and we may be interested in foundation models that go beyond. Self-supervised model was too specific to the training objective, so we didn't want to limit to this. And pre-trained model suggested that the noteworthy action all happened after pre-training. So this basically was the justification that they used in coming up with this new description. Okay, but what does this imply on graphs? So for large language models, we all know what this means, right? So we have a neural model that learns transferable text representations that can generalize to any new, previously unseen text. Now, what could be the analogous definition that we are looking for when it comes to graph foundation models? We're looking for a neural model that also learns transferable representations, but in this case, transferable graph representations that generalize to any new, previously unseen graphs. Of course, these are not formal definitions, so there is a certain level of ambiguity here, and there are many things to decide as to how these things need to be defined, or at least what criteria these models need to satisfy. This is an ongoing discussion, so it's not something that we will conclude in this lecture. But we can say certain specific things, and let's maybe do so. What do we want ideally from a graph foundation model? So what would be the thing that when we have, we will say, okay, it's a great model. Here, ideally, we want to be able to handle different kinds of data sets, yeah, regardless of the types of graphs and regardless of the tasks that we need to solve. This would be amazing. For example, if we have a data set, say the data set Cora, this consists of a single graph. It's a node classification data set, so we are interested in 7-way node classification. It's a citation graph, basically. So the nodes in Cora represent papers, and the connections between nodes represent citations between those papers, right? And so the task is to try to predict the category of the paper. Is the machine learning paper? Is the theoretical computer science paper? And so on and so forth. So it's a simple 7-way node classification task. And the initial features are obtained from the papers, so some bag of word features encoded as 1433 dimensional initial vector embeddings. And we use this, right? So this is one data set, one task, namely node classification task, the part that is highlighted by red. So we want our graph foundation model to handle this. But at the same time, we also want to handle the yellow parts. In this case, we are dealing with FP15K 237, let's say. And this is also a single graph. But in this case, it's a graph without features, and it's a knowledge graph. So Cora was a simple citation graph, an undirected graph, whereas here we're dealing with a knowledge graph, completely different setup, and it doesn't even have features, so that's also another difference. In this case, we are not interested in node classification anymore, but link prediction, completely different task. To make things even more complicated, we can also require, okay, another data set, MUTAC. Now we have 188 graphs, and it's a graph classification data set, yeah? So we have initially also node features on these graphs, 7-dimensional node features. But at the end, we want to classify every graph into 2 classes. So it's Boolean graph classification task. Now you can imagine how hard this is, right? So we want to train one model that can handle all these data sets, all different tasks, and these are just examples, yeah? So we would like to handle many more. Good, so what does this mean? So ideally, we want them to be robust to the type of the input graph, whether it's a simple graph, directed graph, a knowledge graph, a hypergraph. Ideally, we want it to work for all, yeah? The second thing we want is we want it to be robust to the feature type and dimension. So It may be real valued features, right? It may be other types of features. Most importantly, the dimensionality of the features might be different. So in some cases, it may be a 10-dimensional feature. In the other data set, it may be a 100-dimensional feature. And ideally, we would like to be able to handle all of them. And finally, we want it to be robust in the third dimension, which is the task dimension. Whether it's a link prediction task, a classification task, a regression task, ideally, we want to solve all. Good, and what can the classical graph neural networks achieve? So this is what we've discussed a little bit yesterday, and you have seen during the practicals, hopefully got some hands-on experience with graph neural networks. They do apply inductively on any graph, right? So we say this, but when we say this, we have certain assumptions. We assume that the input feature dimensions don't change, the feature domain doesn't change, right? The type of the graph doesn't change, and the task that we're solving doesn't change. Assuming this, yes, we can feed always a completely unseen graph and solve that specified task on that graph. This is fine. But when we change the task, when we change the input dimensions, the feature dimensions, the feature domain, then classical graph neural networks cannot apply on these graphs. Yeah, and that is why we are looking for graph foundation models. Good, and okay, that being said, it's already clear that this is very challenging, right? Like simultaneously trying to solve all of these is quite a hard task. Already solving them individually is somewhat challenging, and now trying to come up with a model that solves all of these tasks is quite challenging. In this lecture, we will do something, let's say, much less ambitious. Instead of trying to come up with such a broad graph foundation model, we will restrict ourselves to knowledge graphs. So there are quite a few works in this direction. So we will discuss knowledge graph foundation models. We are restricting ourselves to certain types of graphs, namely knowledge graphs, and the task will be the link prediction task. But again, we will make it as broad as possible with this limitation, and I will make it clear what it means in a bit. Before we dive into knowledge graph foundation models, maybe a few words about knowledge graphs. These are simple, very simple graph modalities that allow us to encode information about real world. Actually, they are part of many modern information management systems nowadays used for storing and managing relational data. So we can encode information such as, Somalia is a neighbor of Kenya, and Somalia and Kenya are entities here, or things like Nairobi is the capital of Kenya. In this case, we are dealing with graphs that are directed, but more importantly, these relations are now typed, right? So we have capital of relationship, city in relationship, located in relationship, right? So these are typed relations. And they pose, knowledge graphs play a very central role in AI nowadays, and this poses various challenges for AI and ML. For example, we may be interested in constructing knowledge graphs in an automated way using relation extraction or open information extraction, or we may be interested in populating existing knowledge graphs with new facts, new edges, because most of these knowledge graphs are incomplete, and it would be great to complete our knowledge in an automated way, namely growing the knowledge graph. We can also improve some of the information systems using knowledge graphs. For example, recommender systems is an application domain where knowledge graphs are used a lot. Another direction is, okay, can we improve machine learning by learning on top of knowledge graphs? So we may require that the information that we learn somewhat complies with the information that's encoded in the knowledge graphs to reduce things like hallucination in LLMs, for example. And maybe making this more broadly, we can ask whether knowledge graphs can be mediators for developing more reliable and interpretable large language models or foundation models more broadly. Good, let's make this a bit more formal. So we are talking about knowledge graphs, which is defined as shown here. So we have a triple that consists of node sets, edge sets, and the relation types. Yeah, so we don't have features. In this lecture, we assume that knowledge graph doesn't have features, which they usually don't. And instead, we have relation types. Okay, it's a directed edge-labeled multigraph. To give an example, you can consider the knowledge graph shown on the right-hand side of the slide. And we can take just one edge as an example. For example, the capital of Nairobi, Kenya is an edge, also sometimes called fact. And this encodes the information that Nairobi is the capital of Kenya. Here, of course, the capital of is the relation or the relation type. Nairobi is the head entity. This is a convention in the literature. So the entity that appears in the first position of the relation is called the head entity. And the entity that appears in the second position of the relation is called the tail entity. And in this case, Kenya is the tail entity. Okay. Is it clear so far? Are there any questions? Okay, great. Now, I already mentioned that we will focus on link prediction task today. And this is quite important. It's been very prominent in research regarding knowledge graphs, because knowledge graphs are typically highly incomplete, and this makes their downstream use a bit more challenging. And link prediction found many applications in many domains. So for example, in recommender systems, recommending a user something boils down to doing link prediction on knowledge graphs. Again, incompleteness is an issue. There's classical papers that show how incomplete these knowledge graphs are. For example, on Freebase, 71% of individuals lack a connection to a place of birth. Of course, they have a place of birth, but we just don't know it. No? Now, the question is, can we predict new links for the knowledge graph based on the information that's available in the knowledge graph? So the key idea is we don't want to use any textual information, any extraneous information. We just want to rely on the knowledge graph and predict new links based on the existing ones. And why does this make sense? Well, you can look at the example knowledge graph that we have on the right-hand side. We already know, for example, that Somalia, Kenya, and Ethiopia are all neighbors of each other, right? And we know, for example, Kenya and Ethiopia is located in Africa. This information is already encoded. But for instance, based on this information, it may be possible for the model to predict that Somalia is located in Africa. So the arrow, the edge that's drawn in a dashed way indicates the target prediction, for example. So this would be a great prediction, right? Things of this sort can be done by exploiting the structure of the knowledge graph, namely the structure that already is present in the knowledge graph. Good, and how is this problem solved traditionally? So a little bit of a historical context. It started mostly with transductive methods, and the transductive methods are completely out of favor now, but it's important to understand their role. And they were largely inspired by word-to-vec approaches at the time. Word-to-vec had a very transformative effect in deep learning. And they have this very nice figure in this original paper by Mikhailov et al., where they show two-dimensional PCA projections of the skip ground vectors of countries and their capital cities. And the finding is quite interesting. So they're embedding, they're learning embeddings for the capitals of certain cities, right? So basically we have embeddings for cities and capitals. Now, what they find out afterwards is, well, for example, if they take the vector that represents, the embedding that represents Madrid, and subtract the vector Spain, and then add the vector France, then they get a vector that's very close to the vector of Paris. So it's closer to the vector of the embedding of Paris than any other vector in the embedding space. So what does it mean? And this kind of observation generalizes to other things as well. In fact, if you look at this figure, you see that if you take the difference between China and Beijing, that resembles the difference, say, between Poland and Warsaw, or the difference between Portugal and Lisbon, right? So they all look kind of similar. And so they conclude that these representations computed using neural networks, in their cases, they were using neural networks, so these are not shallow embeddings in word-to-vec, are very interesting because the learned vectors explicitly encode certain linguistic regularities and patterns. And in this case, the regularity that they're referring to is the capital of relationship, right? So somehow the model figures out that, Ankara is the capital city of Turkey, implicitly, right? Or Berlin is the capital city of Germany. Good, and the early transductive methods in knowledge graph embeddings used precisely these kinds of ideas. To exemplify one, probably the most popular and canonical example is given by TransE. So the name comes from translational embeddings, and TransE is a very, very simple model. I show this here on an example. So very, very trivial toy knowledge graph on the left-hand side, which essentially just says Kathmandu is the capital of Nepal. So it's a trivial graph that consists of one edge only. And on the right-hand side, we see the embedding space, actually, well, two spaces, but I will explain a bit what that means. What does TransE do? So TransE takes this edge in the knowledge graph, right? Takes all entities and relations. So in this case, we have two entities, Kathmandu and Nepal, and one relation type, which is capital of. All of these are mapped into the embedding space as just like vectors. Yeah? So we treat them as vectors. And the key idea is to make sure that when we sum the vector representation from the head and the relation, we get a vector that's close to the tail. Yeah, so this is the optimization goal in TransE. Yeah, so in this case, what TransE will do is it will take a vector for Kathmandu. Let's inspect the top right configuration. So it will take a vector for Kathmandu. It will take a vector for capital of, and it will try to make sure that when these vectors are added up, it amounts to the vector of Nepal, right? In this case, it intuitively represents that this edge is correct. This information holds. Yeah. Of course, there's no single way of doing this. Many other configurations can satisfy this. You see another configuration down in the first one. It essentially encodes the same information. Yeah. So this is how they operate it. I won't dive too much into the details of these models, because they have a major problem, namely that they can only do predictions on the training knowledge graph. Because we are learning explicitly an embedding for each entity and relation, what happens if we see new cities, right? New countries or completely other things at test time? We have never learned an embedding for those things, so we don't know how to reason about those things, right? So we can only score the likelihood of having a link between entities that we have observed at training time. For all others, we can't do anything. And that's a strong limitation. And graph neural networks, which I classify here as node-inductive methods, basically address this limitation. A quick refresher on message passing neural networks. We have seen this yesterday with a slightly different notation. What were we doing? So we were updating every node feature based on the messages that were flowing from the neighborhood, right? So there was a message function, and then aggregating these messages and computing an update, and we were iterating on this operation. Good. Now, how do we change this architecture that we know, some graph neural network architecture, to make it work with relational graphs now, right? Because the type of the graph has changed. And one important question here is, okay, what is the notion of neighborhood that we should be considering, even, right? Because in a normal graph, yes, you look at the neighbors, this is good. But now, if you look at the neighbors of Nairobi, it has two neighbors, right? Kenya and Africa. But ideally, we would like to distinguish these neighbors because, for example, Africa is a neighbor with respect to the located in type relation, right? Whereas Kenya is a neighbor when we look at capital of or city in relation. So that's why we want to be able to adequately represent the graph and the messages. We want to make the messages to respect the relation types, right, where they flow. So if you are if you're computing a message and flowing it through located in, we want to make this message relation specific, yeah? And that's what the small r in the message function that you see. So whenever we look at the neighborhood of a node now, we looked at the induced neighborhood induced by the relation type r. So in this case, if we are aggregating messages for Nairobi, we will first aggregate for, say, the messages that are flowing from Africa with respect to the located in relation, and then separately, through a different message function, the messages from Kenya. So this is the only major change, right? So we basically adopted the graph neural network architecture to work on relational graphs with the relation types. In fact, if you just take a single relation type, this architecture is essentially the same. Yeah, because then we have only one type of relation. All neighbors are normal neighbors, right? Okay, there is the directedness and undirectedness issue, but if we also assume that these are undirected, it's the same architecture. Good. And RGCN, so this is one of the canonical and earliest graph neural network methods for knowledge graphs, is an instance of relational message passing neural networks. I mean, of course, these models first were proposed and then they were classified as relational message passing neural networks. Now, one thing that we left out and didn't quite explain is, okay, we learned these node representations, pretty much how we discussed yesterday, but how do we do link prediction, right? So, well, that's kind of easy because, at least in the case of relational message passing neural networks, because we have this final representations for each node. Let's say the final representation of node U is ZU, the final representation for node V is ZV, and I'm interested in knowing whether there is a link between U and V with the relation R. Well, I use a decoder. This could be an MLP or any other kind of neural network. I pass these representations that I learned through this decoder, and this decoder is trained to give me a score, right? It tells me how likely is it for these two nodes to have a link between one another, yeah? And it's a directed link. In this case, the decoder is relation specific, so for each relation type that we are making a prediction, we use a different type of decoder. There are many choices for decoder options here or scoring. It doesn't really matter for the purpose of this lecture. Good. Of course, the literature doesn't end here, so there is so many graph neural networks that work on knowledge graphs. It wouldn't be possible to cover here, of course, but I would like to cover at least one other family that also has been very popular. That's initiated by NBF nets, which is then described as a conditional message passing neural network, which is an extension of relational message passing neural networks. What do they do? So the main difference here is related to the fact that here, if you look at this, we are still learning node level representations in the case of relational message passing neural networks. And to be able to predict links, we rely on this decoder that takes two inputs, right, and predicts a score. But this is a little bit strange, right? So ideally, the function that we are aiming to learn is over pairs of nodes, right? So it's a link prediction task, so it's over pairs of nodes. Why don't we encode the information in a pairwise manner in the first place? This relates to the discussion that we had yesterday regarding 2WL and all that, but this is easily becoming intractable, right? So if you want to embed, instead of nodes, every pair of nodes, this is already giving us a quadratic blow-up to start with, and then we have to do operations on top of this. So this is quite intractable, practically speaking. What they have done in this work is quite interesting. It's some sort of trade-off. We don't explicitly encode pairs of relations, but we encode so-called conditional conditional representations. So rather than trying to learn H of V, for example, we learn H of V given a node U and Q. So we fix a source node, let's say U, and the relation type that we are querying for, and then learn the representation relative to this. Now, this also gives us a blow-up, but there are certain computational advantages because this can be parallelized and we don't have to enumerate all the quadratically many things. So there are certain advantages of this from a computational point of view. And the nice takeaway here is that this is achieved with a simple initialization regime. So all that we have to do is we have to distinguish the source node that we want to query for from all the other target nodes. And this is done in a very simple way. So we just initialize everything else with 0 except the source node, which is initialized with 1. There are other choices, but this is a simple trick. And then we do the usual message passing on top of this. And this already gives us a lot more than before. Namely, if we want to now score the link, let's say RUV, how likely is this to be true? What we do is, now that we learned these conditional representations, this already kind of captures this binary information, right? So it already tells us like, what's the chance of having V given that I had U as the starting node and the R as the relation. Now I'm decoding this information. So I'm not relying on the decoder to magically decode the relationship between two things, but I already encode the information into my embedding space, my representation that I've learned, so it's more direct and relies much less on the capabilities of the decoder. Of course, the decoder here can also be many things, including, say, an MLP. In the end, we are still scoring, producing a score for this input. Good. Of course, all the details can be found in the respective papers, and here is an overview from a paper where we show the differences between relational message passing and conditional message passing. They both take the input graph, and in the case of RMPNN, we directly apply a message passing. You can see on the top part. This is the encoder part, right? So the encoder just applies the message passing. And we get, say, two nodes, HU and HV. And these nodes are then passed to the decoder, which is a binary decoder that produces a score, right? And that basically tells us how likely is it to have a link between the node U and V. In the case of CMPNN, the situation is different because we start by this initialization. So we initialize, let's say, every other node with 0 and the source node with 1. And then we do this message passing, which is also a little bit different than the message passing in RMPNN. And once we learn, we already know that this is already conditioned on the node U, right? So we already know that this is not H of V, but H of V given U. And so this can be decoded as if it was a pairwise encoding. And in practice, it works really, really well, much better than RMPNN. It has become pretty much a default tool for link prediction on knowledge graphs. Very, very good architecture, NBF nets. And even the variations of NBF nets work quite well. They also have some scalability issues, but quite mild, I would say. Good, so let's wrap up what we know so far. So if I have a training graph, which is a knowledge graph, then if I'm interested in making a link prediction on this training graph, I can do it using even translational models, right? The transactive methods like TransZ, because everything is observed here. I can also use graph neural networks here. This is fine. But what if my testing graph is completely different from my training graph? Now, in my testing graph, I have new entities, Kathmandu, Nepal, Asia, right? So these are new entities that I've never seen on the training graph. Transactive methods don't apply anymore, yeah? But graph neural networks do, so I can use them. So the existing models can be applied here. This is still fine. Now, what is a bit of a problem is what happens if my testing graph not only has new entities, but also new relation types. What do I do now? Well, now the graph neural network doesn't apply either. Yeah. So if I want to say that Theo is a friend of Alicia and Theo lives in Oxford, and then maybe I want to predict based on this information that Theo visits Vienna, which may be a hard prediction task, but just for the sake of example, it's just not possible. They don't apply. And why? Well, because in this learning regime, the relation types are not really learned. So graph neural networks are inductive on the nodes because they learn embeddings for the nodes based on their structural role in the graph, but the relation types are just randomly initialized during training. Yeah. So if I observe a completely new relation type at inference time, I don't know what to do with this. I can also randomly initialize, but it will produce most likely garbage. Yeah. And this is precisely the idea behind knowledge graph foundation models, because we would like to apply, ideally we would like to be able to train on any knowledge graph and apply to any knowledge graph, even if it has new relation types, even if it's from a completely different domain, right? This is the idea. Good. What we're looking at is being able to transfer certain knowledge from one knowledge graph to another one. So let's say I'm training on the knowledge graph that's shown on the left, which tells things like, okay, there's some bank, HSBC, makes a research on finance, and Oxford makes a research on science, and so on and so forth. And on the right-hand side, I have a test graph, completely showing vocabulary, right? The entities, completely different, relation types are completely different. So now we are talking about Tokyo Electron, supplies Intel, Intel produces CPUs, and so on and so forth. How, first of all, can we hope to transfer any knowledge from one graph to another? Right? That's already a question that we need to answer. And if so, how? Because we never see any of these things before, right? At training time. Well, maybe we can leverage ideas from standard graph neural networks in the sense that they are inductive on nodes, remember? So even if we didn't see those entities before, we can still reason about them. And how do we do that? Well, because we learned in the first place from their structural role, right? So we learned not from the fact that it was it was Oxford, but from the fact that Oxford was connected to science or finance and whatnot. So we learned from the structural role how to embed the entity Oxford. And if the way we embed things, the nodes, if the structural role that they play in a graph is shared between two graphs, then we can transfer this information, right? So if we rely only on the structural information, and there are structural similarities between two graphs, even if the vocabularies are completely different, then we can hope to transfer some of this knowledge. But okay, this is how it's done in the node inductive case in the classical GNNs, but how do we do it with relation types? Now I will describe one model, Ultra, which is one of the first models that did knowledge graph foundation models. And it's quite an interesting, quite relatively simple, but like an interesting approach. How does it work? Now, rather than just initializing the relations randomly, we will try to learn the role that the relations play in the graph. So let's say I have a knowledge graph G, that's given on the left-hand side, right? And I would like to somehow not rely on the fact that this one relation is called R, the other relation is called S, and so on. I don't want to be, rely on this thing. I want to rely on the fact that R and S share a common source, for example, right? They are somewhat sharing a source here, so E1 in this case. Entity is shared between R and S, or R and W, these relations, meet at E3. This is a structural information, right? So I don't care whether it's called R or W. I just care about the fact that they are sharing these properties. Like these kinds of binary interactions between relations, if you wish. And this can be conveniently modeled as binary interactions. Remember, we have this terminology of head and tail. So what we can say is S and R form this path here. So if you look at how they join at E1, at entity 1. So this is the kind of pattern that we are looking at. If you look at the W, so they are forming a tail-to-tail relation, and so do S and R. So their tails meet. That's what the tail-to-tail relation type means. So S and R form a tail-to-tail relation. W forms a tail-to-tail relation with itself. What do W and R form? Well, it forms a head-to-head relation because they're the head entities in relation R and in relation W meet, right? When we look at S and W, well, the head of W is shared with the tail of, head of S is shared with tail of W, right? So what this tells us? This tells us that there are actually, we can maybe use these as fundamental relations, if you wish. So I don't want to rely on the relations themselves, but I would like to rely on how they interact with one another. And this gives me 4 types of relations: tail-tail, head-head, head-tail, and tail-head, right? So these are all the fundamental relations. So what this means is that I can actually construct a metagraph, if you wish, that only encodes this information. So I treat in this metagraph the relations as nodes. So I'm doing a bit of, I'm tweaking things around a little bit, right? So I take the relation R, make it a node in this metagraph, in this new graph. I take the relation S, make it another node, and so on and so forth. And now my relations are the ones that are telling me, oh, how is R related to S? It's related via tail-tail relation, because I know that they meet at the tail, right? This was the idea. And how is R and W related? Well, head-head, and so on and so forth. Now, this gives me a metagraph. What's nice about this metagraph is that it only uses these 4 fundamental relations. And what's the advantage of this? if I learn my relation properties from this graph, then I can do the same trick at inference time, right? Because regardless of how the signature, how the relational vocabulary looks like, I can do the same trick at inference time, and I get these 4 fundamental relations, and I can learn from that metagraph. And again, the idea is the same, right? So if the metagraphs share certain properties, maybe I can transfer this information. Good, and that's precisely what Ultra did. So rather than just randomly initializing the relations and then feeding this to a standard entity encoder, a graph neural network, it uses 2 graph neural networks. One on the metagraph. So on the metagraph, if you see now that our relations are nodes, right? So we can apply a standard GNN to inductively learn on these relations. So we have a relation encoder now. This is a graph neural network, okay? And you can use a RMPNN here or CMPNN. These are all both good options here, okay? Now, what do I do next? Now I already have the relational representations that are learned structurally based on this metagraph. Well, I go back to the original knowledge graph and I apply a standard GNN on it and I initialize the relation embeddings based on what I've learned before. So it's not random anymore, but it relies on the learned embeddings from the relation encoder. And here the choices are also obvious, so I can use another MPNN, CMPNN here. And Ultra uses NBFNet in both cases. Good. So to summarize, what happens is, well, we take a knowledge graph. We have 2 types of encoders now, not just one. One relation encoder that operates on the metagraph that I've described how it's built, and a separate encoder, entity encoder, that operates over the original knowledge graph. And the most important thing here for the entity encoder is that it uses the results of the learned relations from the previous relation encoder, of course, right? And learning this way makes the model also inductive on relation types, and that's exactly what we wanted. So to see why, you can just rename the relations in the input graph, just change the names, and nothing will change because we will get another metagraph which is isomorphic to the original metagraph up to renaming. And so because the names don't matter, the encoding and the whole process will be essentially the same. Yeah, so if you try to do predictions on a graph that's isomorphic, you will actually transfer all of this knowledge. No? So it's kind of a nice property. Good. Any questions so far? Yeah. Yeah. Perfect.
Hi.
Hi.
Do you hear me?
Yes.
Yes. So I've got the questions. The first question is, from the original graph, we are saving only 4 types of relationships: head, tail, tail, head. But are there any possibilities and useful information we can save from maybe common ancestor or something like that, just to keep much more longer weights from 2 nodes,
That's
not only for one iteration?
right. That's a very good question. That's what I will discuss next, actually. Yeah.
All right, good. And another question about the metagraph also. Can you please open the slide where the head tail was presented?
Right.
The question is, we have on the third picture, we have relation from R to W, HH, right? Head. You see?
Yes.
Yes, but why don't we have the same arrow but pointed to the opposite direction from W to R? because they say they have this.
Right. I think we need that too. You're right.
Yes.
Yes, we need that one too. That's missing here. That's correct.
Thank you very much.
Yeah, thank you. Yeah, good spotted. Thank you. Okay, so regarding the first question, so the question, if I am allowed to make it a bit more general, so we rely on this binary interactions between the relations to build the metagraph, right? But this is maybe not the only option, right? So yes, it gives us nice 4 fundamental relations, it's transferable, and it has all these nice properties, but it only looks at pairwise interactions between relations, right? So maybe we can look at different kinds of interactions. And this is related to expressive power discussions that we had yesterday. So I won't dive too deep into this, but just to see what else can be done here. We are essentially using, in the case of ultra, binary motifs, right? So head-to-tail relation is a motif of this form, right? So it gives a relation of type alpha and the beta, and they are connected like this. And tail-to-head is the other way around, tail-to-tail, you know, they meet like this, and so on and so forth. But these are not the only options, so I can do other things. And in fact, this kind of modeling induces certain limitations. So remember the discussion we had about graph distinguishability, it also applies here. So in this particular example, if I just use these binary interactions between 2 relations, I cannot distinguish the relations R1 and R2, and this is the case in ultra. Even though they are different, I can't distinguish them. And this is a limitation that's induced by the fact that I'm limiting myself to learning from binary interactions between relations. What can we do? Well, we can generalize this framework to say, look, we don't need to learn only from the binary interactions. I can just define the motifs that I would like to learn from, right? So these binary interactions can be summarized using these motifs here, these 4 motifs. But I can also have, instead of having this 2 path, I can also have a 3 path, right? So I can have head, tail, tail, right? Head, tail, head. Yeah? So all sorts of options. Of course, the number of motifs as I make this longer keeps on increasing, and it becomes harder and harder to scale. So it's the typical problem that we hit each and every time. But both from a theoretical point of view and also in some cases from a practical point of view, it's useful to know that we are not limited to these fundamental types. In fact, we can define our own motif set, and the rest is the same, right? So we take a different motif set, we do a relation encoder, and then an entity encoder. So same pipeline. And this has actually been studied in this paper of motif, which studies the expressive power of knowledge graph foundation models. And the idea is to generate a metagraph from k-array relations. So say ternary relations, not just binary ones. And turns out that this results in a much more expressive model. And it can, for example, if you use just 3 path motifs, the one that I just mentioned, head, tail, tail, head, tail, head, and so on, then we can distinguish this example that wasn't possible to distinguish in ultra. I highly recommend you to look up the original papers, which I cited at the end of this talk, if you're interested in further details. But just to give a bit of an idea what the implication of the result is, it basically shows that adding motifs generally increases expressivity, and it also gives sufficient conditions, necessary conditions to increase for the motifs to increase expressive power, right? And one example is if I have 3 paths, for example. So if I take longer path motifs, then I get strictly more expressive power. And this is not just limited to 3 paths. If you take 4 paths, you get even more, and so on and so forth. Now, it's not limited to paths either. So instead of looking at interactions between relations in this path form, I can also look at star motifs, right? Actually, I can look at arbitrary things, but it just becomes computationally less and less feasible. In the case of stars, I can look at 3 stars. I mean, 2 stars is a path, right? But 3 stars is not a path. 4 star isn't. And in this case, as I take wider and wider star shapes to build the metagraph, I also get more expressiveness. And this also shows up in an experiment where motif is used with 2 star, 3 star, 4 star, and so on. And the data set is created in a way to reflect this change. And you can see ultra produces 50% accuracy across the board. This is basically random random guess, so it's doing nothing. And the same is true for motif with 2 star, because motif with 2 star is essentially the same as ultra. But as we increase the width of the star that we use in building the metagraph, we start seeing that the problem is being solved each time. And so this is just to say that this can be easily validated on synthetic data. And this is, of course, nowhere near the end of the story, right? So this is only for knowledge graphs and only for the task of link prediction, and you already see that the picture is getting more and more complex. It would be amazing if we can, I mean, there are also developments on normal, simple, undirected graphs. So we also published a paper on triple symmetry networks, which allows us to reason on undirected graphs for both node classification and node regression, regardless of the input dimensions of the node features. So this is quite good. It's already some sort of graph foundation model for node level tasks, but that approach also is lacking some things, and it's not easy to reconcile all of these in a single model. And it's still an ongoing debate what should constitute a graph foundation model. Good, but many promising results, and these graph foundation models, the knowledge graph foundation models, already improve on end-to-end models. So this is very interesting. So end-to-end models which already see the relation types, they can use the relation types, generally do worse than knowledge graph foundation models which don't use these types, because the main advantage of knowledge graph foundation models is I'm not limited to training on a particular knowledge graph. So I can take now, because it doesn't matter which relation types are used, I can take any knowledge graph out there, much like you train an LLM, right? So you take any text out there and you train it on this corpus. Now you can do the same for knowledge graph. So you can take any knowledge graph, regardless of which relational vocabulary it uses, and at test time you can apply it on any knowledge graph without the need of any further training. But we observed, in general, it's also observed in the literature that while this does very, very well, much like LLMs, if you fine-tune a little bit on the downstream task, you do actually much, much better. So this is quite a promising direction in that sense. Many, many developments, so I hope this gives you some inspirations, and I hope you will look into this research directions. Now I can take questions if you have any.
Yeah, cool. Another question. We have extended our relationships to paths more than Average 2, right?
Right.
And is there any results? Like, what was the growth average between the way of the path between going? Because the number of types of the path of the length of M grows exponentially.
Yes.
Store much more information. And what's the best length of the path to be able to build in order to get the maximum results?
Right, so that's a very, very good question. It exactly hints at the problems that we have hit, because as you say, so as you take larger and larger motifs, not just paths, but like larger motifs, then the number of matches you get, like the number of matches you have in the original graph, increases a lot, right? So, and then when you build a metagraph, the size of the metagraph and the number of things, and actually the metagraph becomes a hypergraph in that case, so things complicate a lot. So I would say there is no sweet spot here, right? It really depends on what you are going to do. And taking larger motifs definitely makes your life much, much harder. So from a practical point of view, you're probably still okay using binary motifs. But based on these observations that, you know, binary motifs are somewhat limited, and going higher order motifs seems to be intractable and hard to deal with. We actually wrote another paper on this to say, rather than using prefix motifs, we are taking random walks, and that seems to be doing much better. It's not strictly equivariant, but it's equivariant in probability. So that's a very fresh paper actually, and I think that's the most promising approach so far that I have seen. It also removes the message passing neural network, so it relies on a sequence encoder that's also an interesting aspect of that work.
Great. And are there any references of those papers in the presentation?
To the new one, not, but all the others, yes. But I can share the new one with you.
Yeah, it's possible.
Thank you. Thank you. Yeah, thank you so much.